Okay, so, and I can simply, because I have the value for X, I have the value for omega, I can plot these things. And probably it's going to look like this. Right? What is the frequency of vibration of these things? Like for a peak to peak over here, it is 2 pi over omega. And we know the value of omega, right? That's the time, 2 pi over omega. What is the magnitude over here, like this distance? This is X. And we already found that X is 0.2 F0 divided by K. What about like this point? Okay, this point, if I try to draw the same things, so this is t and this is xt, the function is the same, it is x cosine omega t. This time x is 2.5 f0 divided by k, all right? Because m is 2.5, just some arbitrary numbers I just want to show you. And I know the value of omega, so my graph is going to look like, oh, maybe I can do a better job. All right, so a larger amplitude, so this is now the value x. A larger amplitude, all right, is larger, but the frequency is smaller, or it moves like a slowly. Like from a peak to peak again is 2 pi over omega. And when I'm over here, it means I have a very small omega, all right? Because omega n is the natural frequency of the system, is always constant. Now it is my decision. Do I want a small amplitude of vibration, but very fast motion? Then I design my system to be like around this area. The smaller, the better, because the amplitude of vibration is smaller. But sometimes maybe you care about frequency, which is rare, but maybe sometimes. So as we get closer to 0, the amplitude of vibration is larger, right? And the frequency is smaller. See, it's going to be slow. And of course, when we are at 0, there is no vibration. It's just a flat line, but with a very large amplitude, which is F0 divided by K. All right. So that was the essence of what we talked last time. I hope now it is clear. I re-explain it to make sure that you guys follow. But if you have any question, please feel free to ask. Okay. So again, this is the frequency response. There is no talk about time. It is omega over omega n. All right. And this is what we call magnification factor. What is a magnification factor? It is 1 over 1 minus omega over omega n squared. But we care only about the magnitude of that. So not positive, not negative. So that's why we put it inside this absolute value. And we said when we design something, we'd better be after this square root of 2. Okay, so far clear? And you have all these notes. I'll give you a moment to, if you want to finish writing, please. So this graph can be then a map for us. We know, let's say we have a system, we know what is the frequency of the force. Maybe it's a motor is rotating. Soon we will see examples that, let's say, when a forcing frequency comes from rotation. So we know this omega, we can design K and M, so we can decide on this omega over omega n. All right? So that was one topic that we talked about it. And if you're done, you have no question. The second things that we talked about it was base motion. All right. What is base motion? We said, let's say you have a mass m, And let's say this is suspended from a spring K. And this time, you are moving this point ups and down. Like we call this point the base. So I know the example that I showed you, it was like upside down, but doesn't matter. Intentionally, I draw it like that. So we call this one y, and we said, let's say it is yt, and it's equal to y cosine omega t. Probably when you were kids, you play with yo-yo, right? Imagine your hands moving ups and down, and this m is going ups and down, right? So what we emphasize that pay attention that this is a displacement, not a force. Eventually it transfers to a force because now we have a stiffness, but imagine you build these things, you hold it at the top, and with your hands, you are moving ups and down, like harmonically. So if I want to plot this yt, let's say this is equilibrium, it's going to have a motion like that. All right. Let's say this is time axis. So this is t, and this is yt. So this amplitude is 1. As a result of these ups and downs, this m is going to also vibrate, goes ups and down. And if I draw the, let's say this xt as a function of t, let's go there. So it's going to have a vibration which the frequency is exactly, I'm trying to draw something very similar to that one. But accept it. It's going to have the same frequency as y. So these two have the same frequency. They move ups and down together. All right. But different amplitude. The amplitude of this one, we call it x. All right. And this x had a formula which was, I remember it was y over omega over omega n squared, or k1. No, it was 1. Okay. And this xt is x cosine omega t. Remember, this is cosine omega t. Our excitation is cosine omega t. Our excitation has the amplitude y, right? The system has amplitude x. And the ratio of these two, x over y, it's important for us. Why? Because this ratio determines if m is going to have a bigger or a smaller. So depends on, and we put it inside an absolute value. So the whole thing's here, then it can be something like that. Or so this is xt, and this is time. Right? So it can be a smaller or larger, this x. Smaller or larger than this y. Right? Because they have this relation, and this relation highly depends on what is omega n, and we know omega n depends on k and n, which this function is very similar to the previous function, and we also draw that one, and we realize that these things is exactly the same as the previous one. So depending on where we are on this graph, like what is the ratio of omega over omega n, this x over y can change, right? That makes sense. If you are, let's say here, it is bigger than 1. If you are over there, it is less than 1. And if we are at exactly omega equal to omega n, or omega n equal to 1, then we are in trouble. None of these equation is correct. We are at resonance, and the form of equations is something different, which we discussed about. All right. So remember, on this line, none of these equations are correct because it goes to infinity, mathematically not correct, which we separately discuss about that particular point. It was when we, if you recall, when we said xt has something t sine omega t or cosine omega, I cannot remember the function, but we found something for that line. Right? So this is resonance, which we discussed about. So far clear? All right. And then lastly, what we said also we are interested to know how much force now is being transmitted either to the base. Let's say I'm building these things. I'm interested to know how much force is being transmitted to the point that I'm connecting it to the ceiling. Right? Let's say I built this mechanism and I'm interested to know about force, or I'm interested in knowing about how much force is being transmitted to the mass. So we calculated Ft, stand for force being transmitted. Right? This Ft, we say that it is not minus, it is K x minus y, whatever deflection I'm going to have in this system. All right. So the difference between x and y. So in this example that I show, maybe this is x that we selected, because we tend to select the direction of the coordinate. If I know what is my excitation, like right now it's going up, so we'd better shows like x like that. However, it doesn't matter. If you show the opposite, you just get a negative sign lingering around somewhere with your equation, but the whole things will be correct. So let's say this is y going up, and this is x, the coordinate that I choose. All right. But remember, there is nothing wrong if you choose your coordinate coming down. You can try later. Only things you will end up with equations that has a negative sign, like it's going to look like mx double dot plus kx equal to minus k y cosine omega t. That's going to be the equation. Doesn't matter, because when you put everything inside this absolute value, you get rid of that things. So this is Ft, kx minus y. And when we wrote the equation, if you recall, it was something like this. We said minus k x minus y is equal to mx double dot from free body diagrams, right? Last day when we discussed, we found the equation is like this. We substitute then this one by minus mx double dot. We replace x double dot by these things, which we ended up with mx omega square cosine omega t. And we get rid of that negative sign because we take the derivative twice. We have already a negative, so it's going to be that. So that was a part probably some of you get confused. And it was maybe my fault. You know, that's my motto. Whenever a student don't understand something, it is the teacher's fault, right? Okay, so this force, okay, now I want your attention. This force Ft is not constant, right? This Ft is a function of time. It changes, it goes ups and down, it's harmonic. It has cosine omega t. Sometimes it is 0, sometimes it is at the peak. So it is a function of time. Then we said, well, everything is a function of time here that we are discussing, but we care mainly about the amplitude, how big this force is, because we can base our design based on the maximum. So the amplitude or the magnitude, whatever you want to call it, of Ft is just this portion of it, mx omega squared. All right. And we have the formula for x, which is that y over 1 minus omega n squared, right? This is x. You have all these notes. You don't need to take notes, I guess. And then we have omega squared here. So far clear what happened? So only the amplitude, we get rid of that cosine omega t, not get rid of. For now, we just put it aside. We want to know what is this magnitude, this Ft, mx omega squared. The rest is just some math manipulation. I substitute x by the function that we already found, and we put it there. Then we simplify these things. I guess we divide it by k. It was something mk over k, y, omega n squared. And then we have omega squared here. And after some simplification, ft over, I believe it was ky, gives me, so remember this m over k is 1 over omega n squared, right? Omega n squared, 1 minus omega n squared. Right? Again, this function is important for us because it shows the ratio of the Ft, that's what we call it, the dynamic force or the vibration force, and k multiplied by y, which is what we call it, the static force. Because we have a stiffness, we deflected by y, right? This is y, the amount that we deflected, and there is some amount of force. We are interested to know what is the ratio of these two. Is this bigger than ky, bigger than 1, smaller than 1, too large? And then we plot these things, which, or the FRF for these things, which has a different form. Because the function now is different. Remember, we again care about the absolute value, and it starts this time from 0, go to infinity, and then at very large omega over omega n gets close to 1. So that was the whole story from last day. And I hope now it's clear. Sorry for those who already know, but I had to repeat because there were some questions. Apparently, some people were confused. They were confused, and now I hope it is clear. Okay. So, two different things. Sometimes we apply a force, a harmonic force. Sometimes we apply displacement. Always when we apply displacement, there is a spring between, right? Like similar to this one. The ratio of the force to F0 over K, we call it magnification factor. Or over here, the ratio of X over Y, we call it magnification factor. And one extra thing, we calculated the magnitude or the amplitude of Ft. Now that if I know how large this Ft is, I know how fast this force is going to be applied between these two. And how fast, it depends on omega, right? Because it is a function of cosine omega t. So then I can, of course, calculate the fatigue on this system because, you know, if our force is not constant, it's repeating, it's going to create some fatigue in a system, which that's related to other things. All right, is it clear now, I guess? Hopefully. Now let's continue our business. I'm going to get rid of all of these. And that. And we were here. Now we continue with example 7. All right, example 7, we talk about the mechanism. We have a pendulum, we have a link CD, which doesn't have any mass. We have M2, and then we have this B. If the question didn't, let's say if the question like this one doesn't mention at all about the mass of B, it means that's weightless. If you talk about, let's say, saying this B has this mass, it means we need to also consider its mass. It clearly stated that this CD, we should neglect the mass. Right? And then we said, pay attention to this XB is not a force, it is B cosine omega t, because there is a spring between them. Right? For example, this B can be 10 millimeters, going left and right, left and right. So sort of the base function concept that we explained. But remember, in vibration, those formula that I say, it is always for a spring and mass. Don't rely on that one, because all you need to do when you deal with a problem, draw the free body diagram, and at the end, if everything's go, let's say everything's are correct, you ended up with an equation that looks like this. Like a constant, that constant might be anything. Bunch of numbers, mass, G, like gravity, K, it can have many other things, and F0, a constant. And then the rest, this omega is what we have over here, the function over there. And this X can be X, can be Y, or it can be theta, depends on the variable that is selected. So sometimes system decide for us, like the question decide for us, it says choose the variable theta as it shows. And it shows positive in that direction. But if not, it's totally up to us. You may consider X as the function, okay? Or opposite direction, that's fine. But this is what we have. And then this X, last time we said there should be a relation between X and theta, because remember, we are still in single degree of freedom. If there is not any relation between X and theta, it means something is wrong, because it means two variables and we don't like two variables. Just need one variable. So which is easy to figure it out because it is a small vibration or a small motion. From this triangle, we can write down sine theta is that, and we can write down that X and theta are related like this. This is what we got last time. Now let's draw the free body diagram. So if I draw the free body diagram, so for this M2, right, let's say I have a tension that it's coming from this link. It's more like a cable, or let's call it T for now. And the reaction of this T obviously is going to be on the other side of this link. Or let's say after we move it there, it's going to be messy. Let me not be lazy and draw things nicely here. And in your exam, you'd better like draw the free body diagrams clearly. All right, so this is for that link. And by the way, since now I believe everybody is here, the your exam is next Monday, right? During the lecture, we start at 11 prompt. You have 45 minutes, 3 questions. It's going to be from topics 1 and 2, like up to the topics that we cover by the end of today, which is going to be end of this example 8. So the Friday lecture is not going to be included in your exam. And you can have a formula sheet, the formula sheet, a letter size, back and forth, like 2-sided, you can write on it, and you can write whatever you want. Diagrams, graphs, formula, notes, poem, poet. But whatever you want, you can. Song. Yes. Print is also okay. Yes. No limitation. I'm not going to check that. Calculator, you need a calculator, and any calculator is also okay. Question for the exam? Good. And it's going to be simple. If you just do the practice problems that I put on Canvas, like I suggested, plus the quizzes, quiz 1 and quiz 2. And by the way, I'll get back. Quiz 2, one of the questions related to damping, which you don't need to solve that, study that. I put the solution over. Sorry.
In one of the classes, he gave us a bunch of problem shapes, and like even be given question.
If there is something other than those, like in the momentum potential that I remember, I said for box, for tube, for disk, and for a ball. So those you can write in your formula sheet. If there is anything other than those, yes, I will do it. So we don't need to try to memorize anything or be worried about something. Even I mean during your exam, if something is missing, you can just ask them. Purpose is just for you to understand the concept of vibration. And as I said, don't worry about the exam. It's just going to be a simple, fun quiz. Very simple questions, and just do the quiz 1 and 2 and those practice problems. That's all you need to do. If you have any questions, please feel free to email me, or you can come to office hour. You can ask.
Are you going to like force us to solve a specific question, specific method, like we have to use weakness and more?
Not really. Okay. Yeah. So you might sometimes I might ask that specifically draw this equation using Lagrange equation, but no, the answer would be no. I just say find the equation of motion. You are free to use either Lagrange or the Euler's method. But since your marking is not going to be based on the final answer, you might be smart and without writing any, let's say, equation, you just write the final answer. That's not acceptable. I need to know where it comes from. And also free body diagram is important because if you make a mistake, you're not going to lose all the marks, right? So I realized that, oh, you did this maybe silly mistake of this negative sign. So you'd better follow all this step and also be neat when you're writing. Are we good? Clear? All right. So let's draw the free body diagram for this one. O is a point OX, OY. So this is OX and OY. All right. So this one, I'm sure that we need to include weight because weight doesn't have any effect on the pre-tension or compression of the spring. So I have then the weight, that's M1G. And also I have the T. All right. So the box is over here. And this box, the same T, but opposite direction over there. And this spring, the stiffness is K. How much it deflects? So XP to the left, sorry, to the right, minus X. And don't forget, this is M2. Also, we better be organized and shows our coordinate. What is positive, what is negative. So this is positive for us, and this is also positive. Well, this is the free body diagram, and if you get to this point, the rest is just some simple math. So you look at the this guy and say sum of the forces must be equal to m2 x double dot, right? I have minus t plus k xb minus x is equal to m2 x double dot. So that's one equation. Let's keep it for now. Maybe we can use it later because it does not give us too much of things that we like to know. It has a one unknown t. Let's use the other free body diagram. We take a moment about point O and we say it is equal to IO theta double dot, right? The Euler law, because it is fixed at one point. Remember the positive sign here is whatever theta we decided, which it says if I'm rotating that direction, it is positive. So anything that helped this M rotating that direction is going to be positive. Opposite of that is going to be negative. So then it's going to be T multiplied by the distance 2L over 3. Of course, it is 2L over 3 cosine theta, but we know cosine theta, we are going to eventually put it equal to, or let me write it down, right? But cosine theta, if you recall, we said we approximate it by 1. So that's the moment for this t, right? Because remember this vertical distance is, this is 2L over 3. All right, so and that's positive. Then I have the weight. The weight is trying to rotate it in the opposite direction of what we like. So it is MIG multiplied by 2L3 sine theta. IO for a link, we know it is 1 over 3 ML squared, right? That's for a link. And theta double dot is theta double dot. Yes? Oh, this is M1, right? Oh, you're right, because this is center of gravity. Thank you. Thank you. So this is G, and this is L over 2. Right, thanks. Center of mass is L over 2. Okay, so we're good now? I guess so. Now let's simplify things, or you can continue on your own. Well, let's do that quickly. Mass usually is a little bit ugly, but we can deal with it. I can divide everything by L, so it's going to be 2/3 of. I replace T by the previous equation that I found, M2 x double dot all K xb minus x minus m2 x double dot. So this is T. I found T from this equation. I substitute T. I just wanted to get rid of that T. And minus M1 G theta, half of it, is equal to 1 over 3 M1 L theta double. Remember, we divide everything by L. I hope my math is correct. If that's the case, so this x double dot, let's also substitute it by 2L over 3 theta double dot. Remember, we have a relation over here. So let's simplify everything there. So I'm going to have 1/3 of M1L plus 2m 2L/3. Yeah, you need to check my math later, make sure it is correct. Theta double dot plus, then whatever left here, I'm gonna have m1g/2 minus, oh, this one also x, we know it is 2L/3 theta. So it's gonna be 4/9 L. All of that theta is equal to 2k3xp. Please check these things later, make sure that I didn't make mistakes somewhere. But my point here now, we get to the equation that we wish to get, like the standard form, right? What was our standard form? We have it upstairs here. So this is our m, this is our k, and so if I substitute xb by what I have, which is b cosine omega t, then I have my f0 as well. F0 is 2k3b, right? Like the standard form that we have all the formula for calculating the stuff for that. So as you notice, is everything depends on those free body diagram. After you write the equation, the extra work that we did was just some manipulation of the formula, and we got to what we wish to get, right? Question? Good. Good, clear? All right. Okay. So with that, we close today lecture and see you on Friday. Yep, that's it.